Okay. AP Chemistry Notes, pages 73 and 74. We're going to get into some numbers with acids and bases now. Up till now, the first two lessons were mainly theory and reactions and such. Now we're going to look at the numbers, and as you can expect, probably the most common question in the acid-base area is, what's the pH? So we'll start here. How is pH affected when you pour two acids together? Well, essentially what's happening is they're diluting each other. So it's still going to be acidic, of course. And I think if you don't think about the numbers, you would think, well, if you take two acids and mix them, it's going to be more acidic. But you have to realize each acid is diluting the other acid. So it ends up being in between the acidity of each of the two separate gases. Sorry, not gases, but acids. What we need to do here is you need to figure out what is your total moles of either H plus, if it's an acid, or hydroxide if it's a base, because you could pour two bases together as well, and then find your total volume and then divide by that. Now, I mentioned if you mix a strong acid with a weak acid, you can essentially think of this weak acid as just water. The weak acids are typically so weak compared to the strong ones that they're just diluting it. In that case, you can just find out how many moles of strong acid do you have, divide by the new volume, and that'll pretty much do it, like I said right here. All right, first one is not like that. We've got a strong acid HBr and a strong acid HCl. I've got the molarity of each. Just for curiosity, I calculated the pH before they were mixed. So the pH of the HBr, well, if it's 10 to the negative 3 molarity, it's going to be a pH of 3. Notice I added 1 sig fig. And if the HCl is 4.50 times 10 to the negative 4, it's going to be a pH of 3.347. So those are the pHs of the two acids before they were mixed. And as I mentioned earlier, the final pH, once they are mixed, will be in between those. And you can already see it's a 3.122. So anytime you have molarity and volume, it's all for moles. I introduced this idea in the last unit, but it's even more important right now. So you're going to be doing a lot of this calculation. So volume, molarity gives me my moles of HBr, but what I really care about is H plus, which is the same. Volume, molarity gives me moles of HCl. Again, I really care about H plus. Add these two moles together, and you get this as your moles of H plus total. Then you need to find your total volume. So you would take this volume and this volume, add those together, put it into liters, which gives you this. And divide your total moles by the total volume. That gives you your new molarity. pH is always the negative logarithm of the hydrogen ion concentration, and you end up with a 3.122. And it makes sense that that is between the original pHs of 3 and 3.3. All right, next one. In this case, we're going to mix an acid with a base, so they're going to react. They're not just going to dilute each other, but they're going to neutralize each other. So you want to write the net equation, like I talked about in the last lesson when I did the net neutralization reactions. You want to find any excess. Now, if there is excess acid, then you'll calculate how acidic it is. If there's excess base, you'll calculate how basic it is. However, if it is a titration, the whole point of a titration is for the acid and base to neutralize each other. Exactly. So if it's an acid-base neutralization situation in a titration, there is no excess. So in this case, it gets a little complicated. If it was a strong acid and a strong base, we can assume the pH will be neutral in 7. However, if the acid or the base is weak, it gets more complicated, and we'll look at that in a future lesson. As you can imagine, we will spend an entire 2 lessons on titrations. So don't worry about that right now. What we do, if it's not a titration and you mix a strong acid with a strong base, the pH will be determined by whoever is left over and how much is left over. Notice it says this is only good for strong combos. That refers to what I mentioned earlier, where if you have something weak, things are a little more complicated, and we'll look at that later. So we have 30.5 milliliters of 0.750 molar HCl. We're going to mix that with 60 milliliters of 0.2 molar barium hydroxide, so strong acid and strong base. We want to know the pH after they're mixed. So what we have to do is figure out which of the two survives in a significant amount, and then find the molarity and the pH. So since it's a strong acid and strong base, the equation is the typical hydrogen hydroxide forming water. What do you know? Volume, molarity, sulfur moles. Volume, molarity, sulfur moles. Here's my moles of hydrogen, which is the same as the moles of HCl. Here is my moles of hydroxide. That looks like it says O4, but it's hydroxide. Notice you have to be careful. Barium hydroxide gives off 2 hydroxides. So I solved for my moles of barium hydroxide, then I doubled it. I doubled it. I doubled it. Don't forget that. It's just why I recommend you write, when you multiply your volume times your molarity, write the moles of the chemical that it is, then think, is it a 1-to-1 ratio? In this case, no, it's a 1-to-2. So you got to double it to get your moles of hydroxide is 0.0240. And I did this on purpose, such that if you don't double it, you think you have excess hydrogen, which is incorrect. In this case, the amount of hydroxide is greater, so that's the excess. You subtract the 2. So what you're going to do is subtract, things have gotten a little messy here, so I'll highlight it. You subtract this moles of H plus from the moles of hydroxide, and that gives you that many moles of hydroxide left over. You take it, like I have here, divide by the new volume. The new volume is a combination of the 2 before, the 30.5 and the 60 turned into liters. That gives you the molarity of the hydroxide. Now, to go from hydroxide concentration to pH, there are 2 routes, and they both take 2 steps. You can go from hydroxide to hydrogen ion to pH, or you can go from hydroxide to POH to pH. It doesn't really matter, completely your choice. However, I have found that students typically like this version. The math is faster and easier, so I usually do it this way. I refer to it as the alternate way because going to H plus is the way you were likely taught first, but once you know what you're doing, we'll typically do it this way. what I do here. I take the negative log of the hydroxide, that gives me the POH. So that right there is the POH, otherwise known as the power of hydroxide. And then you subtract the POH from 14 to get the pH, and I get 12.09. Now, if you do it the other route, if you go this way, hydroxide to H plus, then to pH, you actually get different sig figs. And that's fine. Don't worry about it. I know how this works. I will not mark you down. The reason that they're different is because the sig fig rule that I taught you at the very first lesson is not entirely the correct rule. If we were using the complete rule, then we would not get different answers. Don't worry about it. Not a big deal. All right, we're now going to look at a big problem. This is one problem, essentially, as you can see, with a lot of work. There's a lot happening here. This is why these notes are only 2 pages, whereas the last 2 lessons have been 4 pages. I added this recently to the notes. This used to not even be in the notes, and it was just a problem that would come up. And I found people weren't ready for it, so I'm going to teach it. Let's say you have to switch between Ka and Kb. In other words, you're given the wrong one. The first thing is you have to realize that you need to make the switch. Then you have to know how to do it. So let's take something weird. Sodium acrylate. Okay, whatever. There it is. And then they give the Ka for acrylic acid. Well, notice acrylate must be C3H3O2 minus 1. It must be some fancy polyatomic ion. And the acid version of that, meaning acrylic acid, must be the same thing with a hydrogen attached to it. So HC3H3O2. So notice acrylic acid and acrylate are conjugates. Now you might say, why do they say sodium acrylate? Why don't they just say acrylate? The reason is because you can't have just a negative ion in solution. You have to have a positive ion too. So you would never find a bottle of acrylate ion solution, but you can find a bottle of sodium acrylate or other things that are related to that. So the sodium is not going to be important for us, but that's how the problem will be presented. Now, what's important here is to realize the chemical of interest is acrylate, this. And that is going to be a weak base. But they didn't give us the Kb for acrylate. They could have, but they didn't. They gave us the Ka for its conjugate, acrylic acid. And so probably the most difficult part here is just recognizing the difference between the two and that you are given the wrong value. Okay, step 1, write a balanced equation. You know, apparently I've changed the notes over the years. Yours probably look a little cleaner than mine. Write a balanced equation showing how aqueous solutions of sodium acrylate are basic. So notice I've gotten rid of the sodium because it's a spectator ion. Here's the acrylate. Since it doesn't have a hydroxide to give off, I'm going to add water, double arrow, and water will donate an H plus to the base, giving us acrylic acid and hydroxide. Let's take a moment to look at something that causes some confusion. People will see this and they'll think, oh, it does have hydroxide. There's hydrogen, there's oxygen, there's hydroxides in there. But it actually doesn't. Hydroxide is a polyatomic ion that is ionically bonded to ions of opposite charge. This is not what this is saying. This is saying C3, H3O2. So you have 3 carbons bonded, and you have some sort of combination of 2 oxygens and 3 hydrogens. So I have no idea what this thing really is. So it would be something like, let's do 2, 3, and that. I'm just going to make something up. Let's just say there's a hydrogen here, and a hydrogen here, and a hydrogen here, and a double bond to an oxygen here, and a single bond to an oxygen here, and some unshared electrons or something like that. I have no idea what this thing really is. And the whole thing, let's say, has a -1 charge. Notice, and I'm just going to go with my made-up molecule here, there is no hydroxide. There is no OH with a -1 charge in here. So hydroxide is not present. So don't go taking this and say, I'm going to remove a hydroxide from that. If it did have hydroxide, it would have been written ... with whatever, with an OH hanging off the end to kind of show you that. Likewise, notice when I wrote my acrylic acid right here, these 3 hydrogens I left trapped, meaning they're not the ones that are going to be given off as an acid, and I left this one hanging off the end. That is important to note. By writing it this way, it is saying it is monoprotic, and the only hydrogen that comes off is this one. These 3 are trapped, and they're intentionally written like this to show that. Okay, back to the problem. So we've got our weak base. It is going to gain a hydrogen from the water to become the conjugate weak acid and give off hydroxide from the water. All right, find the pH, what a surprise, of a solution if we dissolve this many grams of this stuff in enough water to make this volume. Okay, you're given grams, turn grams into moles, no surprise there. We have volume and moles, divide by liters to get molarity, no surprise there. So this is the molarity of the sodium acrylate. And since it gives off 1 sodium and 1 acrylate, it is also the molarity of the acrylate, which is what we really care about, is that this is the molarity of the weak base. Since it's a weak base, do not write a Ka. It's a base, so write a Kb expression. So weak base on the bottom. There's my conjugate weak acid and hydroxide. This equation comes from what I have up here, this one here. So we didn't really need to be told A, but it was a nice way to guide us into this. And since I don't have the Kb value, I have to get it from the Ka. So Kb is going to be 1 times 10 to the negative 14 divided by the conjugate acid Ka. It's got to be the Ka of the conjugate acid of acrylate. It can't be some random weak acid. And we get that this is our Kb. So that is the Kb of acrylate, C3H3O2 minus 1. And now we just go down our normal journey. You'd probably want to do an ice chart, which I didn't bother to do, at which point you have the Kb, you have X for hydroxide and the conjugate acid. We've got a minus X here, but we're going to assume like we always do, and we get an X of 1.9 times 10 to the negative 6. Be careful, realize this represents the hydroxide, not the hydrogen, because this is a weak base problem. Good idea to check the 5% rule, and sure enough, it turns out it's not even close to 5%, it's 0.009%, so we're good there. I'm going to take the negative log of X That gives me my POH. I'm going to subtract that from 14, and that will give me my pH of 8.28. That makes sense because it's basic, and it's not highly basic. It's a weak base. So you can do a bit of a sanity check on your answers right now. Once you realize this is a base, you better get a basic answer in your pH. If you had messed up and you got an acidic answer, that's telling you and warning you something's wrong, and you can go back and fix it. So that's it for this. I don't think there's really anything to say at this point. Just practice. If the problems are complicated, you'll notice I did my numbering thing where I numbered my steps. 1, 2, 3, 4, 5, 6, 7, 8. I recommend you get in the habit of doing that. It'll help you with your understanding. It'll help me give you more partial credit if something gets messed up on an exam. Here we go.